Okay, everybody. So, okay, so today we're going to do the other kind of thermal actuator that we talked about last time. So last time we just did the heated hybrid resistor, and we saw it bulge up after it heated because of thermal expansion. So now we're going to do this this thermal actuator, and let me draw what it looks like. And this is also something that you guys are going to use for your assignment, and you're going to do a sweep on some parameter like length, and you can turn it in on Tuesday. So on this thermal actuator, so it looks like this. It has the one that I had drawn last time. It had, I believe it had 2 beams, but on this one you're going to have 3 beams. So one's like this. Another one is like this. And then the cold arm is like this. So it looks sort of like that. And these are the anchors right here. So this is anchored down to the substrate. And we're going to apply a voltage between these 2 electrodes right here. In this electrode, we're not going to apply any voltage here. Okay. So if you remember last time, we looked at a thermal actuator that looked sort of like this. Yeah, something that looked like that. So that's what we had looked at last time. And you guys were correct in saying that if we applied a voltage between these 2 electrodes, you guys are right in determining what direction it was going to bend, that direction. Because this side would heat up greater than that side, right? But now we're going to do something like this. It's slightly different, but can someone tell me what would be the benefit of doing it this way instead of that way? Any benefit at all?
Greater delta between the cold arm and the hot part. More force.
Yeah. So can you see what he's talking about? So here, the current would go around this direction. Even though this would heat up more so than this side, there's still current flow going through this cold arm, right? And so it is going to heat up. Not as much as that side, but it is going to heat up. When we saw the temperature, so it is going to heat up more than that side. Over here, as the current goes through, this takes this path right here on this way out. There's no current going through this part, okay? So that means that there's going to be a greater difference in temperatures between the cold and the 2 hot arms. Yeah, and that's one of the benefits of doing it that way. Now, why would these 2 arms be a different length? Now remember, we're trying to get this thing to bend in this direction. I mean, would that even matter? I mean, should this anchor be down here to match with this, so you're both the same length? Is there any benefit to that?
Does it help in like a differential force so it doesn't want to buckle the one in the middle, the arm in the middle?
Right. let me see what you're talking about. So as both of these expand, this one will not expand as much, but you think that this one right here may buckle, or have a tendency to buckle? If it didn't bend, it would have that tendency, I think. Yeah, but we have that degree of freedom, so there's going to be some bending. Yeah, see, does anyone else want to take a stab at this? Like why that beam will be shorter?
Well, you need less delta L on the middle beam. If you're going to curve downward, the top beam has to have more delta L than the middle beam. So if you start out shorter, for the same temperature, you'll have less delta L. And it should bend in the preferred direction without any, it's not going to fight the other way.
Yeah, okay, so let me see if I could draw that. So I'll just do it with like really thin beams, like with this right here. So if this is a longer beam and you bend it down this way, and it's attached to the shorter beam, it comes back like this. The thing is that there's going to be differences in lengths, right? So they're both going to experience some delta L, but this delta L for this is going to be greater than this delta L. If the delta L's were the same, right, like if they were the same length, then it would just elongate straight and it wouldn't bend at all, right? So I'm not sure, like, well, I'm pretty sure you can figure out like where is the optimal positioning of this, but probably the more this is closer to that length, it's probably not optimal, and so it probably won't bend as much as it would if it's at that position. And so, all right, so let's put this in there to COMSOL. And also the thermal expansion part is going to be easier than it was for the resistive beam last time. So I'm going to put on here the parameters. Okay, this one has lots of parameters. Okay, and you can sweep any of the parameters here. Okay, but yeah, so any one of the parameters are fair game for sweeping. And again, the nice thing about having parameters is that you can change a parameter and the whole thing can change, especially if everything's linked together. All right, so we're going to do like another color. So this right here, that is D. That's going to be this dimension of the hot arm and the other hot arm, and this piece right there. There's going to be dW, and this is going to be this distance right here. Okay. There's also a gap. The gap is between here. So that's the gap. It's going to be that parameter. And so the gap here is the same as the gap here. Okay. There's also WB. That's the width of the base. So we can call this right here WB. There's going to be a WV, and that's the difference between the two hot arms. So this distance right here, WV, is going to be an L, that's the actuator length. So just the entire length right here, so of the whole thing. That's going to be L. L1 is just the length of the hot arm alone. So the length of the hot arm is going to be L1, and that's going to equal L minus WV, of course. Right? L2 is going to be the length of the shortest hot arm. So this is L2, the length of this arm right here. L3 is the length of this thick part right here. Can you guys make up this text in the back?
I can't see it very good.
You cannot?
It's a little bit bigger.
All right, I started doing writing a little bigger. L4 is the length of the this cold arm part right here. Okay, 3 more. Now, there's going to be some heat transfer coefficients, and this structure right here is basically going to be hovering right over the substrate, okay? And so the air gap between that and the substrate is really small, like maybe 2 microns. But above, you have a lot more air. So there's going to be 2 heat transfer coefficients, and we'll keep those in. And then, of course, you have this voltage, and that's going to be around 15 volts that you're going to apply. Okay, so just to make this a little bigger, this right here is WB. This right here is WV. This is L1. This is L2 of the second hot arm. Here's gap and D, and this is WD. I mean, DW. Okay.
Question about your WV. Should you define that maybe
Oh, wait a minute.
starting at the beginning of the pad and then it becomes 0 and the same length?
You're absolutely correct about that. Yeah, WV is the difference between these 2 lengths. So that difference is just between here and here. That's right. Thanks. Okay, so that's what we're going to key in. So let's get started with that. Okay, so open up your COMSOL, and we're going to go to Model Wizard. It's going to be in 3D, so click 3D. And for this, we're going to go to we're going to go to structural mechanics, thermal stress, open that up, and then click on Joule heating and thermal expansion. Okay. Then add that. And you'll see it appear down here. It adds all this stuff. It adds the structural mechanics, heat transfer, electric current, and the multi-physics. And you'll see that populate on the model. So then go to Study, and then we're going to do Stationary, and then say Done. Great. There we go. Let's change the units to microns right here. Okay. So now let's key in all these parameters. Okay, so for the first one, that's going to be D. Okay, so click on parameters, then tab over, and that's going to be 3 microns. So you got to put that in square brackets, the microns. The next is DW. Do you guys see the 3 back there? A little bit? Okay. 15 microns for DW. And remember, that's the that cold arm dimension. Tab over. The next is gap. And that dimension is going to be 3 microns. The next is WB. That's the width of the base. And that's 10 microns. Then we have WV, right? That's the difference between the hot arm and the cold arm. That difference is going to be 25 microns. I'm sorry, not the hot arm and the cold arm. The 2 hot arms. The difference between those 2 is going to be 25 microns. Next is L, the length of the entire structure. So it's capital L. And that length is 240 microns. Then we have L1. Now, since we've already defined L and WB, we're just going to say L1 equals L minus WB. And now it knows what those values are. For L2, that's going to be, you can call that L1 minus WV. That's the difference between the 2. Because L2 is the length of the second hot arm, the shorter one.
L minus WB.
Yeah, L minus WV. So it's going to be, this is L right here, the length of the whole thing, and that's WV. So then that's just the length of the arm by itself. WV.
You say you put L1 instead of L? Like your L2, you have L1 minus WB?
Oh yeah, because that's going to be the difference. Now I could say L minus WV minus WB. You see what I mean?
The first way it was defined without work was since we moved over to the point, like a whole.
Isn't L1 already taking a WB off?
Yeah.
Isn't L1 plus WB?
I think that's because we changed the length of the WB because it makes the difference between the 2.
Yeah, let me. Okay, so here's what I'm thinking. I'm thinking. So L1 is just this length, right? And then WB is the difference between these, right? Like if you moved this to this edge, then this would move to that edge. And so L2 is just L1 minus WB. Is that right? No?
I think it's just L minus WB.
Well, we have to minus the W.
But the
Yeah.
WB's included
Well, okay, so-
in WB.
So L2, I think you can think of it 2 ways. The L2 is L1, I'm sorry, L minus WB minus WV, or you could say L2, huh?
WB is inside WB.
W what?
WB is all equals W.
Right here?
Yeah, so it already includes the WB.
In the drawing, you have it go past where WB is, so it's included. Is it supposed to be on the solely on the right side of WB, the WB dimension?
Oh, wait, I think he's, no, well, because you're stating that, like say L1, you're subtracting the length of the foot part. So you
Yeah.
have to subtract WV and WB because the foot is with WB.
Oh, so the length of the second foot is also another WB.
Yeah.
Yeah, oh, okay, all right, that works.
And Yeah, so that's what I did right here. I'm just calling this L1 and then minus WV. It probably would have been easier if I just said that that length right here is just L. And then forget the other one, just add that to it. But, okay, so for L3, now that's the length of the wide part of the cold arm, and so that is going to be L minus 2 times WB minus WV minus minus L divided by 48 minus L over 6. That's how this person had defined that one. You don't have to do it that way, okay? You could choose other dimensions. I don't, but maybe they optimize it some kind of way. Okay, so once you highlight it, it appears down here too. You guys can see that. So it's L minus 2 times WB, boy, minus WV, like Victor, minus L over 48, and minus L over 6. Okay? That is L3. L4 is going to be just L divided by 6, capital L over 6. And now this is the heat transfer coefficient. So HTC, and this is going to be to the substrate. So let's put an S here. So HTC underscore S. This is going to be the heat transfer coefficient from the boundaries that are close to the substrate. And that is going to be 0.04. So that's 0.04. And the units are going to be capital W watts divided by parentheses M times capital K, Kelvin. And we're going to have another division here too. So don't worry about the units. We're going to take care of that. So then you do another square bracket. Then you divide all that by 2 microns. And you put microns in the square brackets. So it's basically trying to take into account that it's very close to the substrate, but just 2 microns away. And then when you tab over, you see the units are properly spelled out. See, it has watts divided by meters squared there per Kelvin, which is what you want. So you got a meter here, you got a meter right here, and then you have another meter contribution by dividing it by 2 microns. Okay, so that was the heat transfer coefficient to the substrate. Now you have another heat transfer coefficient, and that's for the upper side, the upper surface. Okay, so for the upper surface, the numerator is the same, but you have a different denominator. So instead of dividing it by 2 microns, we're going to divide it by 100 microns. So, oh, sorry. Yeah, it's US, upper surface. So it only corresponds to the top surface, okay? Because that has more exposure, like more atmosphere is exposed to, so different heat transfer coefficient there. So 0.04 square bracket capital W divided by parentheses meter times Kelvin, parentheses, square bracket. But this time we're going to divide it by 100 microns. And then put microns in square brackets. Okay? So this one should be 20,000. This one should be 400. And then for our voltage that we're going to apply, so put dV, D for delta, delta V, and we're going to put 15 volts. Put volts in square brackets, and capital V for volts. Okay? So how are we doing? Everyone good? Now also remember, we did this at the very first time we put in parameters, but we haven't done it since then. You could type in descriptions. You know, you put in heat, you know, transfer coefficient here to just remind you what those things are. Okay. But for those things, I've drawn it over here. Hopefully that'll make more sense by showing you the picture for those other things. Okay, so now that we're done with that, let's start making the geometry. So go to, click on Geometry 1, and then right click on it, and then add a work plane. Okay? And then click on the work plane. And now we're going to add lots of rectangles. As you can see, there's lots of rectangles we're going to add. But we're going to add them in here by always selecting rectangle, and we're going to key in our geometries that we have defined. Okay? So right click on plane geometry, and then click rectangle. Yeah, so click on rectangle. For the first one, make the width L3, make the height dW, as you can see here, right? And as for positioning, just change the X, make it L minus L3, and then build that. You might have to zoom out. Yeah. Okay. So that's the cold arm. Okay. Now go back to geometry again. I'm sorry. Go to work. No, wait a minute. Go to plane geometry. Right click on plane geometry and add another rectangle. Here's our second rectangle. Okay? And for the second rectangle, put in L4 and D right here. So L4 and then D. And then for X, put in L minus L3 minus L4. And for Y, put in DW minus D. And then build all. Zoom out. Okay, so you have the wide part of the cold arm, and then the skinnier part of the cold arm. Okay? And again, that's L4 over here. Oh yeah, and also you guys can rename these things. Like for example, if you like click on rectangle 1, if you highlight it and then go down to rename, you can call that cold arm wide, and then enter, and it'll change the name right here to cold arm wide. And then right here you can rename it to say cold arm fin. Then cold arm fin. Like that. You see what I'm saying? Because we're going to end up with lots of rectangles, you might forget like which is which. So if that happens, you can rename your rectangles to make them make more sense to you. So go to plane geometry again, another rectangle. Now for this third rectangle, enter in WB as in boy and DW. So WB and then DW. And for the X position, put in L minus L3 minus L4 minus WB. So L minus L3 minus L4 minus WB, and leave Y alone and build all. Okay, zoom out. Okay, so that's going to be our first anchor right there in the cold. Plane geometry, another rectangle. So this is the fourth rectangle. Put in L2 and D. L2, D. And for X, put in L minus L2. And for Y, put in WD plus gap. Okay, build all. That's going to be the first hot arm. Okay? And you can see here how they made Y be WD plus gap. So it has to go up WD and go up some more gap to get that spacing between the two. Then of course the nice thing about it is if anyone wants to parameterize the gap, it'll change the gap of both of those, right? So that's why it's good to parameterize your stuff. So let's go to another rectangle. So this is going to be our fifth rectangle. And so for this one, put in WB for the first thing, and for the second one, put in DW plus gap plus D. So DW plus gap plus D. And for X, put in L minus L2 minus WB. And then nothing for Y. Let's build that. And that's just the other anchor right here. Now for our sixth rectangle, add another rectangle. For that one, put in L1 and D. And then for the positioning, put in L minus L1 for X. L minus L1. And then for Y, put in DW plus D plus 2 times the gap. So DW plus D plus 2 times gap, build all. And now that's the long hot arm. And I zoom out. We're almost there. Another rectangle. For the seventh rectangle, put in WB and then put in DW plus gap plus D. DW plus gap plus D. And for the positioning, for X only, put in DW plus D plus 2 times the gap. DW plus D plus 2 times gap, build all. Hey, wait, that didn't work out. trying to figure out where my error is right now. Oh, I'm sorry, X is 0. So copy that, cut it out, and paste it for WY. There we go. X is 0. Build all. Here we go. Okay, couple more. Yeah, we have 2 more to make. And now we're going to do the coupling between the two, the connectors, little small ones. So another rectangle, and this is going to be our 8th one. So just type in D and gap. So we knew the height's going to be gap, right? And for X, put in L minus D. And for Y, put in DW plus gap plus D and build all. And that placed that little tiny piece right there. So one more. Another rectangle. This is our last rectangle we're going to do. Well, I shouldn't say the last rectangle. there's going to be the underside of that, but that's going to be short. Put in D and gap, and then put in L minus D and DW, and then build all. Here we go. So that's the top part of the structure. Now we're going to unionize the whole thing. So go to plane geometry, right click on it, go down to Boolean, go to union, okay, and click here, click in that grid and do Control All. You want to select everything, and do not keep interior boundaries, so unselect that, and then build all. And then you can see that everything is now one solid structure. Okay. Now the next thing we're going to do is, this happens all the time in lots of microstructures, is that you don't end up with very sharp vertices. There's always some a fillet. So we're going to put our fillets in here. So go to plane geometry, right click on it, click on fillet, and now we're going to select all of our fillets. One thing you can do is click on the grid and say Control All, but there's some fillets that are not needed. Like, let me move this up a little bit. Maybe it can get larger. Like I'll zoom in. Yeah, so if you click on this, see, that's not going to be a fillet. So every time you click on a point, it'll like highlight blue, or you can toggle it off and it'll just go to a black dot, a smaller black dot. So click on every straightaway. So here's something that's straight. That's not going to be a fillet. Those two are not going to be fillets, right? These right here on the edges, those are not going to be fillets. So you can turn them all off. I mean, you may have to enlarge that over there. So these I'm going to turn off. That's off, 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 off. No fillets. But that one in the corner, that's going to be a fillet. Let me see, what else do I need? Oh, there's one right here, I think. Yeah. Let me zoom in and get that. Let's turn that one off. Okay, I think that's it. If not, it'll complain, right? So build all. Oh, I forgot the radius. Radius is going to be D over 3. So remember D's like the width of those beams right there. So D over 3 is going to be that, build all. So one of them it didn't like. Which one is that?
On the straightaway. Click. Click and fill it 30 minutes.
Which one was it? Oh, I think it's this one right here. Yeah, so let me unselect that one and try it again. Build all. Okay, yeah, there we go. So no complaints that time. And I didn't try this, but I think even if you do have a warning, that shouldn't mess up the simulation. I don't see why it would do that, but it's just some error checking. Okay, so now that we've done the fillets, let's move on. Okay, so now we're going to extrude it to 3D. So 3D is in geometry. So right click on geometry, go down to extrude, and we're going to extrude it by 2 microns. So you just got to put 2 there, and then I guess you click on that. Yeah, didn't just do build all. And as you can see, it's now 3D, 2 microns. Okay, so now what we're going to do next is underneath. So this is like a top view, but underneath these structures right here, like underneath this pad, I'll try to make a 3D view of that pad here. There's like a little piece that goes down. Like that. Okay? This little piece it exists under each of these pads right there. Also under here, it's very common when people make microstructures to make little dimples. Okay? And what the dimples do is they keep this structure from adhering to the substrate. Because if it's open to the atmosphere, there could be some humidity that builds up, and you're going to have these meniscus forces that if there's some liquid there, it's going to cause this structure to attach to the substrate and not let go. Because remember, it's very flimsy and out of plane direction. So we're going to have some dimples underneath there, and we're going to put these hubs there too. We're going to apply the voltages on the bottom. So these are the parts that are actually on the substrate itself, and they're like 2 microns wide. And that comes from this, because remember we talked about last time, a few weeks ago, is that when you have this substrate right here, you typically have some sacrificial material, right? Then you add some photoresist polymer. You have a mask here that has a hole in it. Like here's the mask with a hole in it. You shine some light through here, and it breaks the bonds, on the polymer. And then so what happens is that you can develop this with this other type of chemical that will remove the material that has broken bonds, leave the other material behind. And then that is like connecting to some hard substrate. Then you come and then you lay down your material. So this is the material that you want is laid down like that, and then you get rid of this sacrificial material right here. That just goes away, and that's why these structures. Well, I went over too far with this, but just like maybe just to here. And that's why these structures here, they have little connectors right here that go down to the substrate. anyways, that's the reason behind that. Oh yeah, and for the dimples, let me just explain that real quick. So for the dimples, what's happening here is, let's say you have another structure over here with dimples. You have your sacrificial material, and you do a timed etch. Oh yeah, and I should say on Tuesday, we're actually going to do some chemical processing. We're going to run a simulation, and it's going to go through some diffusion, and it's going to etch away some material, and you'll see how that works. So it's kind of related to this stuff. So you do a timed etch, and then you etch away some material like that. And then you lay down your polysilicon on there, right? And then you get rid of your sacrificial material. And so there's like a little space here, but it's like a dimple. So if this ever goes down to the substrate, the surface area is so small, it's not enough to keep it down to the substrate, and so it'll come back up. So that's the idea of the dimples. Okay, so let's go to a second work plane. So let's go to geometry, and we're going to add another work plane. And this is going to be the work plane for the dimples in the anchor. Okay? And so let's go to our plane geometry, and it's showing where this other thing is. It's like a projection onto it. So go to plane geometry, add another rectangle. So we're going to add a few of these. So the width here is going to be WB minus 2 times D. WB, boy, minus 2 times D. And for the height, it's going to be 2.5 times WB minus 2 times D. The X is easy, that's just lowercase d. The Y, wow. You're not gonna like this. The Y is the Y is DW plus D plus 2 times gap, close parentheses, plus parentheses. Those parentheses are just like to separate things. You're not multiplying anything with that further parentheses. DW plus gap plus D, close parentheses, minus 2.5 times these parentheses, and this is going to be WB, like boy, times 2 times D, close parentheses, minus D. Okay? And I'll read that again. So the first parentheses is DW plus D plus 2 times gap. The second parentheses is DW plus gap plus D. And the last part is minus 2.5 times parentheses WB minus 2 times D parentheses minus D. And let's build that. And I put that little thing right there. A lot of work for a little rectangle. But again, if you guys wanted to, you could have went to sketch and just drawn your rectangle. like for example, you can just go here and then oh wait, I don't know if the resolution is what we need yet. Yeah, because if I draw a rectangle, it like snaps to a grid. Yeah, that's not going to be what I want. Let me get rid of that. Yeah, that's not gonna be good. Okay, so anyway, it copied all my my deletions.
Did you click that rectangle now? Okay.
Yeah, so I guess what I can do is just get rid of this. Are you sure? Yes. Okay, yeah, so all we have is a rectangle 1. Okay, so now let's do a build all. Oh, I delete these too? I guess so. Yeah, if we made our resolution better, we wouldn't have that we wouldn't have that problem that we're dealing with right now. Okay, so let's go to plane geometry and add another rectangle. And this other rectangle is going to be WB minus 2 times D. And then, it's going to be the same size. So let's go over to the other one, just copy and paste. So copy that, Control C, and then paste it right here. They're all the same size. But they're at different locations. So the X location is going to be L minus L2 minus WB plus D. And Y is just going to be D. And build all. And place it right there. Okay? And then our last rectangle is going to be on this one right there. So let's go to plane geometry, do another rectangle. And we're just going to paste what we had in that clipboard. Let's go over here and get our width, copy and paste. And for X, we have L minus L3 minus L4 minus WB, boy, and then plus D. And for the Y, it's just D. And build all. Okay? Now for our dimples, let's do some fillets here too. So let's zoom in and we're gonna do fillets on those things. Okay, so go to plane geometry, go to fillet. If I can find it, right here. Go to fillet, and then click on all the fillets. You can do highlight if you want. Like this is the select box, so you can select that. You can come over here and select. Click it again. Click it, select those, and click it again and select these right here. And then for the radius, it'll be D over 3 again, and build all. Okay?
Can I get the positions of the rectangles again?
Huh?
Positions of the X, Y, of the rectangles again?
Oh yeah, okay, so the position of the X and Y?
Yeah.
Yeah, here we go. So for the third one, we have L minus L3 minus L4 minus WB plus D. And Y is D, of course. For the second rectangle, we have L minus L2 minus WB plus D. And rectangle 1 is really long. Do you need that one too?
I got one.
Okay, cool.
What was he doing again?
Oh, 2? Right here. L minus L2 minus WB plus D.
Got it.
Cool. Okay, so now let's do the dimples. So we can zoom out again. Yeah.
What was the radius of the fillet?
Oh, it was, the fillet radius, D over 3. Okay, so yes, let's do the circles. So go to plane geometry, right click, and let's do a circle right here at the top. And these are going to be our little dimples. And so as for the radius, put in d over 2 for the radius. And then for the position, put in x. For x, put in L minus L3 divided by 4. And for y, put in dw divided by 2. And then build all. Then it puts a little circle there. Okay, and for the other ones, there's going to be 2 more circles that we want to put there, but what we can do is just, I think we can just copy, like, oh yeah, we could just do an array. So go to plane geometry, go to transforms, and then go to an array, okay? And then this is the one we want right here. So click on that, and now populate it into the objects that we want to have an array with. And we want 3 of them. We want one right. We want to keep this one, put one right here, put another one right there. So with that in mind, we want to say our array size is going to be 3 in the x direction, 1 in the y. The displacement is going to be L3, uppercase L, L3 over 4. Yeah, and this is build all. Oops. I'm sorry, it's supposed to be negative L3. Okay, let's do that again. Put negative L3 and then build all. There we go. Yeah, it was going the wrong direction. But basically, remember L3 is the length of this whole thing. So L3 over 4 is basically a fourth of it. So that's why we went down this direction, L3 over 4, each of those times. Okay, so now let's do an extrusion of that. So go to our geometry, and then go to extrude, and click W2, and we want to extrude 2 microns. We'll put in negative 2 microns. So there's negative 2, and then build all. And then it should be like that. This is what it looks underneath after you build all. And then go to geometry, and then you want to unionize the entire thing. So go to Boolean, go to union, and then click in here and do Control A. And so you should have like 2 things in here. This first one and that second one. So it's really like the stuff from underneath there. See that? So it includes both of those. And then remove keep interior boundaries, and then say build all. So now the whole thing is one structure. Huh? Oh, so this last step, you mean like the union step? Okay, so the union step, what we did is we went to geometry, and then we went to Boolean, and then over to union. That's how we got that. And then when we got to union, we clicked on here and did Control A, and that's how we got those 2 things, ext1 and ext2, in our input objects. You unclick interior boundaries, and then you say build all. Okay?
I missed something on the extrusion for the little parts.
Oh, okay. So on the extrusion, where are we at with that? That was right. Oh, right here. Yeah. So here's the extrusion part. So like when you go to geometry, you want to go to your extrude thing, right? And then you click on your plane that you want to extrude on. And in our case, it was this plane right here. And then we put in -2 for that direction.
Okay.
So, yeah. Yeah, so now, so let's label the thing that's going to be in the substrate. So let's go to definitions. So go to definitions, and we're going to make a label for something. So go to selection and say explicit. And then what we'll do is we'll change this to boundary. And what we'll do is all the things that's going to like touch the substrate, we want to put in here. So make sure this is highlighted. In my case, it's pink. And then you click on it, and then it puts that boundary number into your box. So make sure it's pink, and then click on it, highlight it, click on it, and you may have to zoom in for like maybe the dimples. And you want to make sure it's pink because if you move your cursor around, you might end up pointing to another side by accident. Okay?
Do you want the dimples to touch the substrate?
Yeah. Okay, it's not really in real life touching the substrate, but what we're going to do is we're going to make the dimples be a roller. Okay, so the anchors are going to be fixed, but the dimples are going to be like have like a roller boundary condition.
Okay.
Yeah, that's why we're doing that. Yeah. Okay, so you got all those in, and then name it substrate, and that's all you got to do here. So next time we click substrate, it'll just highlight all that stuff. That's the reason why. Now let's add a material. So let's go over to here and click add material. Oh, it's already up for me. So go to MEMS, go to semiconductors, and then click on polysilicon. And then click on the plus button, and it'll add polysilicon. And we're not going to do all the stuff we did last time. All we're going to do is change the electrical conductivity. So for this, just put in, I think it's 5E4. Yeah, 5E4. The conductivity for polysilicon is doped. Okay. Everybody caught up with me? Okay, so now let's go to the solid mechanics and let's fix the anchors. So I'll zoom extents. Let's go to solid mechanics and then right click on it and then say fix constraint. And let's select these things right here. So that's anchored, that's fixed and anchored, and this right here is fixed and anchored. Okay. Now we're going to do rollers. Okay, so go to solid mechanics and right click on it. And this time, instead of clicking fixed constraint, click roller. And then let's enlarge the dimples. And then click on the dimples, make them pink and then click on it. Make it pink and click on, and make it pink and click on it. And those are going to be our roller constraints right there. So it's like, they'll be gliding on a surface with no friction. That's the idea. Now let's go to heat transfer. And let's go to heat flux. So remember, we have two heat flux types of things, right? So for the first one is like parts that are close to the substrate. So click on all boundaries, okay? We're going to remove the top boundary, but for now click on all boundaries, go to the top boundary, and what you're going to have to do is cycle through until you get to the top boundary and then unselect it. So I'll do zoom extents, and then just go through every single one of them until it becomes green. For me, it's number 4. Okay, because we're going to do that one separate next. So for number 4, click minus, and then come down to convective heat. So this is convection. And then type in our HTC_S. So those are the portions that's close to the boundary. Then do heat flux again for our next one. And for this one, just click 4. So boundary. Oops, wait a minute. Just click on the boundary. So 4 should only appear here. And for this one, type in HTC_upper side. So US. Okay. Now let's go to the physics. Yeah.
I'm having some issue like actually selecting the boundary.
Oh, it's
So
gonna-
I click on it. Yeah, right there.
Yeah, so click on that, and then go to select all boundaries. Yeah, and then why is it not? It's not it's strange. That's an error. Okay, so let's do that in a few minutes. I'll come back to you because we're just going to be a couple of minutes over for those of you who can stay. So we only have to do the. I think we just have to do the. Oh yeah, so let's do the temperature. So go to heat transfer, go to temperature, and then click on substrate. That's what we named before, substrate. And that's going to be our temperature of the substrate. Okay? So we don't have to click on those boundaries. Yeah.
Where did the substrate?
Oh, we named it up here. We went to explicit. So we went to definitions, and then we named substrate right here. Yeah. Yeah, so remember when we were clicking on the boundary, I mean the bottoms of all that? Yeah, we just named it substrate. You can name it something else if you like. So that's our substrate temperature. Now let's go to electric currents. And then let's make a ground. So click on ground. And then make this one right here the ground. So click on that. And then let's pick the voltage. So let's click on voltage. Electric potential. And then let's click on this to be the electric potential. And let's call that dV, capital DV. And now let's go to our mesh. And let's click on free tetrahedral. Let's go to our size and pick fine for our size. And then build all. And then that's what our mesh should look like right here. Okay? Then once you do that, I think you're good to go with solving. Yeah, so then go to study and then click on compute.
What size is
Oh, fine. Yeah. Yeah, so this is what it should look like when you get done. And there's some kind of deflection. Now, initially shows von Mises stress. So what we can do is this. We can say, we can go to our stress, and then go to our surface, and then go into here, and then make it show plot deflection instead. So let's go to solid mechanics, go to displacement, and then click on this right here, double click on that, and then plot that. Now that's going to be the total deflection of everything. Okay? And if you want to see temperature, just click on the temperature one, and you'll see where the temperatures are. And which is really good because both the hot arms got really hot, right? And the cold stayed pretty cold, except for up here at the top, it got a little warm, but all of this remained, quite cool, relatively, with respect to the hot arms. Okay. Now, oh yeah, one last thing I want to do is the parameter sweep, what you guys will do. So to do a parameter sweep, go to study and go to parameter sweep right here. Right click on study, say parametric sweep. Okay. Click on the plus button right here, and it adds something to sweep. You can click on many things, it'll sweep through all of them. Okay, but let's pick, and it allows us to sweep any of our parameters. So for example, if we want to pick L, the length of the whole thing, we can do that. And then for the next one right here, click on the range. So you can do it two ways. You can do it by range, and you just fill out this table right here where you're starting, where your steps are, where you stop at, or you can just enter in the values one by one, separated by spaces or commas. So for example, I could do it this way. I could say like 240 microns, 260, 280 microns, if I want to do it that way. Or I could put in a range where I start at 240 microns, my step is 20 microns, and I stop at, let's say, 280 microns. Okay, and I could do a replace or add, and it'll do that. And now if I say compute, it'll take a little longer, but not, much longer. But what it'll do, it'll sweep the L parameter, and it'll show you different values for length for each one of those. Okay, so see how it got a little longer? So here's a shorter one right here, and here's a really short one. So that's the 240, here's a 260, and there's the 280, like that. So that's how you sweep various parameters. Okay. So I know you need help, John. So anything else before we cut out? All right. I'll save this and I'll put it on I'll just upload it, because I know some of you had to leave early, but you're not here now to hear me say this. I'll email everyone. Okay, I'll save this online, on the canvas, and you guys could play around with this and play around with the parameters. So let me do this.